Hello and welcome to an all-new episode of SGAC Japan Space Talk. I'm your host Taka, and Samashima is on the screen right there. And today we are going to welcome a very wonderful guest. He is Dr. Matthew Richardson from Australia. Welcome and thank you for being here.
Thanks for having me.
So a quick guest profile, Dr. Richardson is a rocket scientist from Australia. After receiving his PhD at the University of Tokyo and JAXA last year, he's currently an assistant professor in the Global Initiatives team in the School of Engineering, University of Tokyo. Now, could you give us a quick introduction of your upbringing and what you do now?
Sure. So I am originally from Australia. I graduated with a degree in engineering in 2011, and then I started working in Australia as a systems engineer in the aerospace industry. And I worked for almost 5 years in that job. And I started to become a little bit bored because the job wasn't really engineering. There's not much of an aerospace industry in Australia, or at least at that time, there wasn't much happening. So the job was a lot of paperwork and not a lot of problem solving. And so I decided I wanted to do something, I guess, more challenging. So I signed up for a PhD program at the University of Tokyo. That was 2016. So I came over to Japan, researched at a lab in JAXA while I was at Tokyo, then graduated last year and started working at the university.
What initially sparked your interest in rocket science? Was that always your sort of your field, or?
I think what started it, it's what I studied as an undergraduate. It's not what I was doing when I was working. But I think what it was I always sort of wanted to be working on, the fastest vehicles and the coolest technology and the most advanced things. And if you sort of think about that perspective of just focusing on the coolest technology, I guess rockets was always at the top of the list. They're the fastest things we make. They're, very technologically advanced, so that's what I wanted to focus on. And then when I looked more and more into it, I sort of really, really enjoyed it. The actual engineering analysis that's involved in, designing and analyzing and testing rockets. So it started off just, I think, being like a vanity thing where I'm like, I just want to work on the coolest technology, but I actually really enjoy it. So that was fortunate.
It's cool that they say, oh, it's not rocket science, but the fact that you're actually doing rocket science.
Yeah, I get that a lot. Yeah, it's I mean, there's that, and they talk about it's not brain surgery either. And I don't know much about brain surgery, but to me, it looks a lot more difficult than what I do.
Yeah, I would guess so. So in your 5 years work as a systems engineer, what was the system that you were working on? You said it was not very aerospace.
No, so I worked, well, it was aeronautical engineering, not space engineering. So aerospace engineering is aeronautical and space, but that was more focused on aeronautical engineering. I was working for a company in Australia that does aerospace and defense. That's a typical sort of combination of industries to focus on. The company is an Australian company. It's actually called Nova. It's not the same as the Japanese Nova. Obviously, very different company. But Nova in Australia works, like I said, both on defense and aerospace more generally. So I worked on many, many different types of aircraft, essentially, helicopters, commercial jets, smaller general aviation aircraft, we call them. Basically, what we did most of the time was designing modifications for those aircraft and making sure that they were sort of compliant with the regulations. And that compliance paperwork was most of the job, which is not that exciting.
So in your PhD and your current research, you focus on rocket propulsion. Could you talk more deeply about your research field?
My PhD research was exclusively focused on rocket propulsion. So JAXA has a small research program focusing on reusable launch vehicles, like what SpaceX is doing, basically trying to make a rocket that can launch and then land and then be reused. So I was in that lab focusing specifically on extending the life of a rocket engine, because rocket engines, more so than any other type of combustion engine, are exposed to some really, really extreme operating conditions, specifically high temperatures, high pressures, that sort of thing, which wears the rockets out very quickly. So even if you can recover the vehicle, the engine itself might be very, very badly damaged. So we were focused on how to minimize the severity of those operating conditions, lower temperatures, lower pressures, that sort of thing, without reducing the performance of the rocket. That's specifically what I was focused on, and trying to quantify how much of that would extend the life of the rocket. How many more flight cycles could it achieve? That was my PhD research. At the moment, I'm working on a new project with JAXA that's focused on combined cycle propulsion, which is a sort of a combination of rocket propulsion and jet propulsion. That's a very new project, so I'm not sure how much I can say about that. Some detail has been published, so I can put a link in the chat, but it's in Japanese, so you can read a little bit about the project we're working on there. But like I said, it's very new, so I'm not really sure how much I'm allowed to discuss it.
Oh, so it's like some next level government stuff.
No, well, it's just, I think the group that I work in, the research group at JAXA, they're not prolific publishers. They don't publish a lot of papers. They don't do a lot of PR. So I don't want to, I guess, go out there and talk all about what they're doing if they're not comfortable with it. So it's not like a regulation or a rule that's preventing me from doing this. It's more of a professional courtesy. But if you are interested, there is some good information in that link. It's basically we're working on developing an engine that can operate as a rocket at higher speeds, but at lower speeds, it also has a more traditional fan engine, almost like a turbofan that you'd see in a jet. But the operating concept is a bit different. It doesn't actually combust. It doesn't actually use a turbine, an air turbine. It uses more of a rocket turbine. So, yeah, like I said, it's an interesting idea, and it could really improve the low speed efficiency of a launch vehicle. That's the big advantage, but it's very, very early days.
Can we talk a little bit more in more detail about the reusable rocket engines? I think that's been a really hot topic in the past 5-10 years, especially now that we've seen SpaceX achieve it. What is the biggest setback in using reusable rocket engines, and how did they achieve it?
It probably depends who you ask. A rocket is obviously a very complex piece of technology, so there's a lot of experts involved, right? Someone like me who focuses almost exclusively on the engine. You've got people who focus on the guidance and control systems. You've got people who focus on the structure and the thermal protection. And I'm pretty sure everyone would say that they have the sort of most important, most challenging job. So I would be biased if I said that it was the engines. But in reality, I think the biggest barrier until now has been recovery. So how do you get the rocket back? Because especially if you're launching into orbit, you have to attain these really, really high speeds, and they sort of has to be almost horizontal, which means your rocket is traveling very fast and very far away from the launch site. So how do you get it to come back, or how do you recover it? Which is why you always see them fishing rockets out of the ocean, basically, because they're crashing into the ocean hundreds of miles away from where they launched. So that recovery has always been a challenge. It's a very difficult control problem as well. So this vertical landing that you see, these propulsive landings they do, I've heard as a scale, you can compare it to taking a pencil and throwing it over the Empire State Building and having the pencil sort of land on its head. That's the scale of the problem they're talking about in terms of how far it has to go, how fast it has to go, and how accurately it has to land. So it's a very, very difficult control problem. It's very difficult to control a rocket throttle, and it's even more difficult to sort of gimbal it and keep the rocket sort of steady as it's coming down. So that is an incredibly difficult challenge, but it's a challenge that is being solved. So SpaceX are doing it. Other companies are starting to do it as well. So it's definitely not impossible.
But I mean, we've seen SpaceX achieve it, but before that, they've had quite a few failures in the process.
Yeah,
Right?
yeah. So that's sort of SpaceX's philosophy almost for development. It's that their approach is trial and error essentially. They're not deliberately failing, but there's an acceptance and a tolerance of risk, I think, at SpaceX, which is how they're trying to move quickly. You know, they're trying to take some risks, maybe lose some rockets every now and again, but advance much quicker because they're willing to take those risks. By contrast, if you see a company like Blue Origin, their development philosophy is much more conservative. They don't want to have failures. They don't want to learn from failure. They want to get it right the first time, which means, I mean, it could be equally effective as a development process, but it's a lot slower, which is why you're seeing, I think, Blue Origin is taking a lot longer to get to the same point that SpaceX is
at. Right. Are there any other barriers when it comes to reusing rockets? As you mentioned, extreme temperatures. Does that wear out the materials that are used in the engine and whatnot?
The temperatures is probably I think one of the biggest challenges, because if you're exposed to high pressures or high aerodynamic loads, for example, as an engineer, I think you can always just reinforce whatever you're building. You know, you can make your structure stronger or thicker or whatever. There's a weight penalty that you'll pay, but you can always just make it stronger. You can't just make something more temperature resistant, right? You can try and use more thermally resistant alloys in your structure or in your engine, but there's always a limit to that. You can't just keep making it more and more temperature resistant. That's sort of a physical constraint.
Right, and I'd assume rockets already have sort of modified up to its fullest potential already when it comes to temperature resistance, pressure resistance, and things like that.
Yeah. So I mean, it's rockets have always been sort of at the cutting edge of technology. They're right at the sort of using the most advanced materials and using the most advanced technology. So it's really hard to push beyond that. It's sort of a very slow process. But I mean, I think one of the philosophies that I was looking at as part of my PhD was maybe we shouldn't be pushing these things as hard as we push them. Maybe we can get almost the same level of performance with a significant reduction in the sort of harshness of that operating environment. So don't punish the engine so much, basically, and maybe we could still get almost the same performance.
And how exactly would we achieve that?
So without going into all of the math and the equations, the things that affects the performance of a rocket generally, so there's two metrics that we use, right? There's thrust, which is the force that it generates, and there's specific impulse, which is how much force it generates per kilogram of fuel that it's burning, which is basically a measure of efficiency. And so those two are very closely tied together, but the sort of things that influence them are the type of propellant. Different propellants are better than others, and that's generally related to the molecular weight of the exhaust gases. So molecular weight exhaust gases are more high performance, which is why hydrogen is such a good rocket fuel, because it's a very simple atom, very small atom. Temperature affects the performance of a rocket, but it's sort of a square root relationship. So doubling the temperature will not double the thrust, for example. Pressure is much more directly related. I don't think it's a linear relationship. from memory, but there's a much stronger correlation there. So my whole argument at the start of my PhD, at least, was let's focus on the temperature, because it is a hard limit, like we talked about before, and it's also not necessarily has a bigger impact on engine performance. When we built a very complex simulation model of a rocket engine, and you sort of plug in all the data and you run it under different conditions, you find that it's not as simple as just adjusting the temperature. Everything is sort of interconnected. But what we actually found was the way you change the temperature is you change the mixture ratio, you change the ratio of fuel and oxidizer. But when you do that, you're not, after the combustion reaction occurs, you're not just changing the temperature, you're changing the composition of the gas, which means the gas has a different thermal conductivity, it has a different heat transfer coefficient. All of that changes, and that sort of tips the equation in the opposite direction to what I was expecting. So even though actually increasing the temperature is almost better, because if you increase the temperature, the gas properties change such that the heat transfer into the walls of the engine slows down. So that was the big thing that surprised me. All of these adjustments we're talking about are very minor. So we're talking about making, like a 5 or 10% change in some of these factors, in temperature or in pressure or something. But they can have quite a big effect on the overall life of the engine. We found that some of these changes could extend engine life by 40 or 50% in some instances.
Wow. So can I ask a question? So you said, a lot of these changes are sort of minor in this field. My understanding, I'm not an expert in rocket, obviously, but what I recently see is this shift of like previously, a lot of rockets maybe use like oxygen and hydrogen, but like recently, some companies are like starting to use methane instead. How does that like actually change this paradigm of like rockets? Like, does it change? Is it like a complete game changer, or is it like, why is this like shift occurring right now?
It is an interesting change. I think that's one of the ironic things when people talk about rocket fuel as this sort of generic term, when in reality, rockets have the most diverse range of fuels of almost any vehicle, all jets in the world basically use the same fuel. There's minor differences between military jets and commercial jets and American jets and non-American jets, but it's basically all the same. Basically all cars use very similar fuels. They're either all diesel or all unleaded gasoline or whatever. But rockets, there's so many different types of fuels that you can run a rocket on. And the trend towards methane is interesting. I don't know what's really that innovative about it. I think if you're talking about SpaceX in particular and the development of Raptor, I think a big factor there has been that they can produce methane on Mars, and they're thinking decades ahead to when they're using these starships for interplanetary transport, and they have to have some sort of fuel source out there. There is a process you can use to generate methane on the surface of Mars, which, if you have a methane-fueled rocket, that gives you more capability, I guess, to refuel out there. If you go even further out to Titan, I don't know if Starship could make it to Titan. They've certainly shown videos of it getting all the way out to Saturn, but that's just an artist impression. But Titan obviously has a very high methane content in its atmosphere. So methane is, I think the thinking is methane's easier to find in deep space, at least for SpaceX. But hydrogen is everywhere as well. I mean, there's volatiles on almost any planetary body, which you can crack and get the hydrogen and the oxygen out of it. So in terms of its utility as a fuel, the big weakness of hydrogen, I guess, is its density. So even in a liquid state, in a sort of cryogenic, high pressure, low temperature storage state, hydrogen weighs 70 kilograms per cubic meter. So for comparison, water is 1,000 kilograms per cubic meter. So it's very, very light, which means you need a very, very big tank to store a lot of it. Methane is not incredibly dense either, but it's more dense than hydrogen. So it's easier to store methane cryogenically than it is to store hydrogen. It doesn't leak as much as hydrogen does. So it's really that it's a trade-off. And hydrogen, the benefit of hydrogen, like we talked about before, is this low molecular weight, but that's also the weakness, because that low molecular weight translates to a lower density. It means it's more susceptible to leaking and boiling off and this sort of thing. So it's a double-edged sword. And I think that the calculus at the moment is that methane, if you look at those other advantages of methane, not necessarily just related to how well it performs in the rocket exhaust, maybe those benefits outweigh the benefits of hydrogen.
Interesting. Well, one thing I've heard is that like methane, it's like clean burning, so you like it doesn't like produce any like carbon residuals like after the burning. So that makes it like easier to perform maintenance on the engines. I don't know if that's right, but
I think, well, it does generate CO2 emissions. But I think the concern there might be more related to things like black carbon and particles and soot, which is really only a concern for solid rockets, because they use solid rockets operate very differently from liquid rockets, but they have to include all sorts of chemicals that aren't propellants, basically, to hold the solid fuel together. So basically like glue, like binders and these stabilizing chemicals and this sort of stuff. So they have incredibly dirty exhausts, basically, because all of that stuff is coming out with the propellant. Liquid rockets you don't really need to use any sort of additives or any of that sort of stuff to the fuel. So generally liquid rocket engines burn cleaner. The cleanest burning fuel is hydrogen, because a hydrogen oxygen exhaust gas plume is mostly water vapor. Most exhaust gas plumes are mostly water vapor, but there's no carbon. There are some other chemicals there as well, like hydroxyl and stuff, depending on the mixture ratio, but it's mostly water vapor. So in that sense, I guess hydrogen is the cleanest, but all liquid fuels are cleaner than solid fuels.
Speaking of cleaner fuels, I read recently that ships are getting criticism for using fuel that is sort of toxic to the environment, and that article was saying that maybe rockets in the near future might be facing similar criticisms.
Yeah. So, I mean, maybe a bit off topic, but ships use what they call bunker oil, which is like the lowest quality, cheapest, dirtiest petroleum product in existence, basically. And because they burn that incredibly filthy fuel, basically, because it's very cheap, the emissions are incredible. Like there are ships going around the Mediterranean, I think, that produce more CO2 emissions than like 50 million cars or something, like insane numbers like that. In terms of the exhaust emission issues with rockets, until now, the exhaust themselves haven't been that much of an issue, because if you look at the life cycle emissions of any process, generally speaking, a sort of single catastrophic event like a rocket launch is not as significant as a more long-term process. So even though a rocket launch releases a lot of gas, it only does it for a few minutes, whereas manufacturing the rocket takes months and months and months, and it uses a lot of energy, it uses a lot of materials and processes, and the manufacturing of the rocket generates a lot more emissions than the actual rocket itself. So that's been true up until now, but if we start to look at reusable rockets, then you only have to manufacture them once, and you can use them many, many times. So going forward, emissions might be an issue. But generally speaking, rockets are such a small industry that I think they've flown under the radar. Now that could change too. I mean, if we start sending millions and millions of people to Mars or something, then that's going to require a lot more transport than what we're doing at the moment. But it's been largely ignored up until now because it is such a small industry. You know, rockets launch maybe once a month or something. You know, it's nothing compared to even aviation. So.
Right. And can you talk a little bit more about the combined cycle propulsion and how that might affect the future rocket launches?
So one of the biggest problems with using rockets generally is that they're very adaptable engines in that they can work in basically any environment, in an atmosphere, outside an atmosphere, at low speeds, at high speeds. The envelope in which they can operate is very, very large, but they're also very, very inefficient. So we have to use them because they're the only engines that have an envelope that extends into space at orbital velocities. So we have to use rockets because they're the only engines that can get us all the way there. But if you were trying to, say, fly like a normal airplane from one city to another, using a rocket would be a really bad idea because it's so inefficient, because it burns so much propellant. And the reason for that is it carries the propellant with it. So once again, that's an advantage and a disadvantage. Because you carry all of your propellant, you can go anywhere at any speed, but you have to carry that propellant. A jet engine, on the other hand, carries some fuel, but most of the propellant is the air that it's pumping through the engine. So because you don't have to carry that propellant with you, it's much more efficient. The specific impulse that we talked about before, for even a hydrogen engine, which is hydrogen-oxygen engine, most efficient type of chemical rocket engine, that's about 400 seconds in the best case scenario, maybe 450. A jet engine, if you use the same metric, specific impulse, the specific impulse can be thousands and thousands of seconds. It's like an order of magnitude more efficient. The problem is that you can't use jet engines where there's no air, and you can't use them at very high speeds because the faster you go, the hotter the air gets, and you need the air to be cold so that you can combust it and add energy to it. And if it's already hot, then you can't add much energy to it, so it's not really that useful. And it starts to reach the temperature limits of the engine. So jet engines are more efficient, but they can't go as fast. Rocket engines can go very fast, but they're not efficient. So the idea behind combined cycle engines is to use a jet engine at low speed, basically, and then change to a rocket engine at a higher speed. There's many, many different ways to do this. In my bachelor's degree, I looked at a hybrid engine that would go from being a classic turbojet engine to a ramjet engine, and then finally seal off and become a rocket engine at high speeds. There's a company in the UK working on an engine called the Sabre engine for a space plane called Skylon. They've got a very interesting combined cycle system planned as well. And the one that JAXA is working on is basically a turbofan. So it uses a big fan to compress air with an afterburner. But the fan itself is driven by a turbine that's run using rocket propellants, which basically means you don't need an air combustion chamber, which makes it sort of maybe less efficient than a full jet engine, but it also makes it easier to control and probably a bit simpler to design. But you still get a very, very big performance increase from doing that. Well, that's what the calculations show us anyway, because it's, like I said, it's a very early project and we're only doing simulations at this stage.
Right. Okay, thank you for your insights. We would like to move on to the Q&A session. So, dear participants, you can leave your comments in English or Japanese, what you would like to ask Matt.
日本語でも英語でもコメントを受け付けてますので書いてください。So then I guess I'll ask you the first question. So you mentioned, you know, there's these different philosophies between companies like SpaceX, Blue Origin, and whatnot. Which startups or these rocket companies, including SpaceX, which philosophy do you like the best? Do you prefer?
I think with a lot of things in rocket science, you've sort of got to be a bit agnostic. You can't really say, I prefer this option or I like this option. I mean, if you want to achieve success, you've sort of just got to go with whatever works, and you've got to be sort of prepared to adapt. Like personally, I really like hydrogen as a fuel because it is so clean burning. But if people are moving away from that because the benefits outweigh the benefits of methane, for example, outweigh the benefits of hydrogen, then you have to go in that direction. With that in mind, if you look at the different approaches of Blue Origin and SpaceX, I mean, SpaceX started first, so that might be one reason why they're so far ahead, but they do seem to be advancing very, very quickly at the same time. Whereas Blue Origin, they've done some launches, some suborbital stuff. They've got plans for a big orbital rocket, but it's still just a plan, you know, like SpaceX just seem to be moving at breakneck pace just because they're not afraid to make mistakes. And that seems to be moving the ball forward faster. So I guess that's probably the better approach.
Okay. Well, I mean, like Blue Origin, like they don't really, show anything or provide any information to us. So like it's sort of like mysterious,
That's another difference between the two companies, I think. SpaceX are very open and they like to, communicate and show the public what they're doing, whereas Blue Origin are a bit secretive, and they like to let their work do the talking, is what they'll often say, things along those lines. They don't want to talk themselves up. They want to just demonstrate that they can do things and let that be proof of, I guess, their accomplishments.
I just realized, speaking of rocket startups, are you aware of the company in Japan, the startup in Japan that's like trying to build a rocket?
Stello Technologies, is that it?
Yep.
Yeah.
Do you know anything about that startup or like any insights?
Mostly just what I've read in the news, which has not been good news for them. Mostly, they've had some problems, some pretty spectacular failures as well. But yeah, I'm not really familiar with them. I'm not sure how closely they're working with JAXA. I think there is some involvement there, but it is mostly, I think JAXA is not really that connected to the project. It's a very private, commercial venture, I guess.
Okay. Like coming from a foreign country, from Japan, like, do you see any like hurdles of like starting a startup in Japan or like doing space business or just anything in Japan, like from like a foreign perspective?
I'm actually really impressed with the startup scene in Japan, the space startup scene. You've got companies like, iSpace and Axel Space, and they seem to be very, very flexible. And like one of the big concerns and one of the big issues that I have with working in Japan generally is that sort of in business and working environments, there's a lot of conservative sort of fear of change, right? Like they don't want to do anything different, and they don't want to, potentially fail. And there's a lot of risk aversion there. And that really holds a lot of places back because they're just not willing to adapt and change. But the space startups in Japan are very different, I think. They have a much more modern outlook on business. And I think it actually creates a really big opportunity for them. The funding is also very impressive. So despite that sort of traditional conservative risk aversion, the Japanese finance industry seems very willing to fund a lot of these ventures, which is very important. I mean, if you talk to any startup people, they're always focused on getting financing. That's the number one thing. And that seems to be available in Japan on a level that I would never expect to see somewhere in Australia, for example. I can't see Australian banks giving hundreds of millions of dollars to a space startup company, but it seems to be possible in Japan. So I think there's a lot of opportunities, not a lot of barriers in Japan for private enterprise at least.
Well, that's pretty interesting. Well, I'm living in the U.S. right now, and obviously, the United States is, like the hotspot of anything related to space. But like, my impression was like these sort of not westernized, but Western countries, like including Australia, like tend to like fund these sort of more than like Japan or like other Asian countries, I guess. But like that's not really the case in Australia then.
Yeah, Australia's a special case, I think. The United States might be different, but just the economics of Australia sort of make it very difficult for anything high risk or high technology generally to be funded, because so much of the economy is based on mining and real estate and these sort of ventures that are very profitable and mostly very stable.
Mm-hmm.
So they're not really that interested in taking risks on big tech startups and that sort of thing.
Okay.
That's my impression at least. So the US might be very different. Obviously, there's
Yeah.
Silicon Valley and that sort of
Mm-hmm.
thing. It's a sort of bigger, more diverse economy, but yeah, not in Australia.
Okay, well, you now have the space agency, so that might, potentially change the paradigm.
Yeah, and there are startups in Australia. There are definitely people who want to make it happen, but people is just one part of the equation, and money is a very big part too. And the money might be the issue for a lot of Australian startups.
Okay.
We have a question. Is there any advantages in studying reusable engines in Japan? What is unique point of Japanese propulsion development? In terms of budget, the US has much more for rocket development. That's why I asked the question.
It's a very good question. Personally, there are some advantages for me in that when I came to Japan, so I came from a defense industry background in Australia. I'm used to everything having sort of limits on what I can do and how I can work, and security concerns and getting a security clearance, and security clearance in particular. I was Australian, so it wasn't a problem, but when I applied for my security clearance, I have to say my wife is not Australian, and so I got a whole bunch of questions about, well, where is your wife from? Do any of her relatives work for a foreign government? And all these sort of things, like very, very strict citizenship sort of focused questions when they're talking about these security issues. I know it's very similar in the US if you want to work on rockets in particular, because rockets, in terms of technology, are basically indistinguishable from missiles. So rockets are very easy to weaponize. So they're treated as sort of a weapon technology, and the security implications around that are very tight. So for example, if you want to work for SpaceX in an engineering role, you go on their website and look for the jobs. You'll see them every now and again. They advertise for a lot of people, but all the engineering jobs will basically require you to be a US citizen, because that's the only way that you can work in that environment because of the security regulations. It's a very similar thing, I think, even in research in America. So if you're going to work for a university, or I don't even think you can technically work for NASA if you're not a US citizen. I think you have to be a contractor to work there. But the citizenship issue would have created a lot of barriers to me doing anything meaningful with rocket engine technology. Those limitations don't exist in Japan, which I was sort of very impressed by. There was one time where I couldn't participate in an experiment because there were security concerns. And basically they said, sorry, we can't let any foreigners on this project. And I understood, given the context of the project, that was completely understandable. But that was the only time that I ever felt as a foreigner that I couldn't do something in my research. I was always given access to all the data that I needed, all the information and resources. And I think that would have been very difficult to do in any country that I'm not a citizen of, because most countries have these security restrictions in place that basically treat anyone who's foreign as not secure. So that was a big personal advantage for me. In terms of the research that's happening in Japan, it's been happening for a very, very long time. basically more than 20 years at this point, Japan has been doing the sort of testing that you've seen SpaceX do for the past eight to 10 years. Japan was doing that in the late 90s. Not at the same scale, much smaller scale sort of experiments, but there's a long history of a sort of very small but dedicated team of Japanese researchers who have been working on reusable rockets for a very long time. And that was attractive to me as well.
Okay, thank you. Are there any other questions? Oh, she says thank you.
So if I'm correct, no, so I think there's no questions right now. Yeah. Going back to what you do right now, do you teach rocket science, or is it what are you doing right now, basically?
So, like I said, I do some research, but most of my job is teaching. I'm at the School of Engineering, but I'm not technically in the Department of Aeronautics. So I work for an education center within the School of Engineering. So it's not actually part of any of the individual departments. So what we teach is generally more generic topics about one of our most popular courses is how to write scientific papers in English.
Okay.
And we run those sorts of more general courses that are focused on internationalizing the School of Engineering. So bringing more foreign students in and supporting them, and also giving Japanese students the skills that they need to sort of function in a global academic environment. Having said that, one of the courses we run is a project-based learning course, where students can choose many different types of projects under this course, and they have many different supervisors. If you're aware of Formula SAE, that's the university race car project. Basically, every university in the world has a team in the Formula SAE competition where the students build a small race car. That project at Tokyo is run through this class. So that's more of a mechanical automotive engineering project, but there's a whole range of these different projects. And this year we've started one for satellite design. We're competing in the satellite design contest, which is a Japanese competition that's organized by a lot of different sponsors. So we've started that this semester. We've got 4 teams, about 20 students involved. So I'm excited to see how that goes, because all of our teams are very enthusiastic. So yeah, I mean, my job is technically to internationalize engineering education, basically. But as part of that, I can sort of take these angles on it and propose these projects that are more space focused, because I think space it's obviously a very international sector, and these sorts of international bilateral or multilateral missions and projects are becoming more and more common, more and more popular. So it's sort of fertile ground for focusing on that sort of on these sorts of projects.
Speaking of internationalization, we have a question in Japanese. I'll read it in Japanese and I'll translate it just for clarification. これからも日本に残るつもりですか？また、もし日本の学生に物申したいことがあったら教えてほしいです。
Monomo. I'm sorry, I don't know what monomo means.
Okay, so the first question is, do you plan on staying in Japan going forward? And the second question is, do you have any comments towards Japanese students? Comments or messages?
Staying in Japan, yeah, I'd like to, but I'm not sure. The job that I have now is it's a tokunin job. So that's, I think in the US you'd say it's adjunct faculty. So it's basically not a tenured position. It's a 5-year limited position. After that, I mean, it depends on family as well. So I'm married. My wife's Japanese, but she really enjoys living in Australia. So I'll have to consider that. But I think it's in terms of my career, Japan is a very exciting place to be. I feel like I said, my old job in Australia, I got bored with. I'm not getting bored here. Like sometimes I get very frustrated and very stressed, but I never get bored. So it is very exciting to be here, and so that's definitely an appeal. In terms of, is it a message for Japanese students? Is that what that means? Or,
Yeah, message or comments.
Maybe in like a little bit in a negative context, maybe.
Like criticism.
Yeah, sort of. I mean, or it could be a positive message, but either ways.
I think for a long time, I had an image of Japanese students as sort of being maybe hardworking, but not, I don't know what the right word is. If they set a goal, they work towards it very hard, but sometimes they can be a bit wary of stepping outside their comfort zone, I guess. More of that cultural sort of risk aversion, I think. I think that's sort of true, but not true. Like the more that I interact with Japanese students, and maybe this is sampling bias, like a lot of the students that I work with are very motivated to try new things, and they're not afraid to, do things differently. So I find that very, very impressive. But I don't know. My experience can be colored by the fact that most of my interactions are with UTokyo students. And I like to say that UTokyo as an organization is sort of magnifies everything about Japanese universities. The good things are much better and the bad things are much worse. So everything, I think that really sort of colors what I see, because I haven't had much interaction with students from other universities, but I would really be interested to do that.
Okay, next question. What makes human-related rockets different? What took the US so many years since the space shuttle to develop a rocket to finally get humans to space, other than the policy governance-related restrictions?
So the policy and governance-related restrictions are a big part of that. The basic fact is there wasn't really a stable succession plan, right? I think it was, I'm trying to remember an interview, it might have been with Neil deGrasse Tyson, where he said the reason that so many people were emotional at the last shuttle launch, like they were saying farewell to something and that it was such a sad moment, was because there was nothing sitting on the launch pad next to it. There was no successor. Like if we had a shuttle 2.0 or a brand new rocket for people to focus on, people wouldn't be so upset about seeing the old one retire. Like no one gets upset about their old car when they buy a new car because they can focus on the new car, right? That these programs take decades and decades to sort of develop. The space shuttle was initially proposed by Richard Nixon, who was the president in the early 70s. Early 70s is when they started working on the project, or maybe even late 60s. And the first flight wasn't until the 1980s. So it took a very long time for it to develop. And things are only getting slower and slower and longer and longer. Even uncrewed missions are taking decades to sort of develop now. So the fact that there was no long-term plan in place, well, there was a plan, but it kept getting changed. And those changes basically delayed it to the point where they had to retire the shuttles without the replacement ready. In terms of the technical issues, a lot of the technology is basically the same, at least from my perspective. The propulsive technology is the same. The big difference is the risk tolerance. If you want to launch humans from a rocket, you have to be much more concerned about not having it fail. Obviously, the big technical differences are at the top end of the rocket, right? That's where the life support systems are, and that's where the re-entry capsule is, and that's where all the human spaceflight hardware is. I'm more focused on the bottom end of the rocket where the engine is. And in that case, there's not much technical difference between a human-rated rocket and a non-human-rated rocket, other than the reliability.
Right, thank you. Okay, I'm going on to the next one. Nice to see you again, and thank you for your lecture. It's by Watanabe. I have a quick question for you. Are there any projects between Japan and Australia, or are you willing to join collaborative projects for space development? You know, Australian Space Agency has been founded in 2018, and I'm pretty sure that Australia is really interested in space development. So could you tell me your opinions?
Yeah, look, I'd love to do a collaborative project between Australia and Japan. I think there's a lot of potential because we have, if you look at the sort of our the industry and the geographic differences between Australia and Japan, there's a lot of, I guess, synergy is the right word. There's areas where Australia doesn't have a lot of strength, but Japan does, and vice versa. I mean, Hayabusa is a perfect example of that. There's no way Australia could have done Hayabusa mission by themselves, but it would have been very difficult for the Hayabusa capsule to re-enter over Japan, just because it's a very small area of land and very densely populated, whereas Woomera was a perfect site for that. There are other areas, I think, where we have sort of complementary interests. Specifically in my field, Japan has, over the past 20 or 30 years, sort of become a global leader in liquid rocket engines, in particular in hydrogen-fueled liquid rocket engines. The engines that have been developed for, H2 are some of the best in the world, some of the best hydrogen engines. Australia doesn't really have the technical capability, the knowledge, or the industrial base to build rocket engines and liquid rocket engines. But Australian universities are global leaders in hypersonics and scramjet engines, which is like what we were talking about before, air-breathing engines that could potentially be much more efficient than using a rocket engine. But scramjet engines only have a limited flight range. They can't operate when they're going too slow, and they can't operate when they're going too fast. So to fly a scramjet, you still need a rocket to basically act as a booster. So if you're thinking about a next generation launch vehicle that might use a scramjet engine, you're still going to need rockets. So I would love to see a project between Australia and Japan where the Japanese side developed the rocket engines and the Australian side developed the scramjet, and together we could make a really, really efficient next generation launch vehicle. That's the dream. I don't know how to make it happen.
You know if the governments are in talks right now for potential projects?
For that project in particular, I know they're not. We've tried to get them to talk, but maybe one day. There is a memorandum of understanding that has been signed between the Australian Space Agency and JAXA. The Australian Space Agency is very new, and it's very different in its focus to JAXA. So JAXA is much more of a comprehensive organization, like a mini NASA, not the same scale as NASA, but JAXA is focused on everything, right? There's space science, there's human space flight, there's Earth observation, aerospace technology, they're doing everything. The Australian Space Agency has a much more narrow focus. They're more focused on sort of these key areas where they think Australia can be a global leader. So they don't want to focus on things where there's other countries, richer countries with bigger organizations who can do things better. They want to find these sort of niche areas where they can be the best at what they're doing in the world to attract international partners to work with them. So the Australian Space Agency, it's good that it exists, but it has a very limited and narrow focus. So it's about, if you're an Australian and you want the agency to focus on your work and your project, you really have to campaign that, hey, look, we can be the best in the world at this sort of narrow area. I think that's politically, that's the key to getting support from the Australian Space Agency.
Next question. In the context of the US government switching to SpaceX contracts from Soyuz, I have a question. The space shuttle was a reusable design and had some difficulties related to complexity and cost. Why do you think the reusable mindset of SpaceX is more feasible now? Primarily technological advancement, or perhaps was their approach, or our approach to reusability flawed?
I think technology is a big part of it. And as part of that, like I said before, one of the big lessons of the shuttle for me personally is you have to focus on the best solution. You can't focus on the solution that you like the most. And a lot of people, including myself, really like the shuttle because it's such a cool spaceship. It's got wings and it flies around, it comes back down and lands. Like, it's just really cool. A capsule is not really that cool. I mean, a capsule is just a thing that sits on top of a rocket and just falls back down. It's not cool, but it works, and it works really well, and it's really reliable, and it's really efficient. So focusing on the best technology is important, the best solutions. There were other problems with the shuttle too. So it was reusable, and it was envisaged that reusability would lower costs. But like a lot of NASA projects, it's sort of spread out a lot, right? You know, the boosters were made in one state, the tanks were made in another, everything's assembled and brought to Florida for the launch. Like, it's just all over the place. There are multiple different contractors. The contractors never had any incentive in their contracts to try and improve efficiency. You know, it was all these cost plus contracts, which is basically you just got whatever it cost you to do your job plus 5% or 10% or whatever the profit margin was. So there was no, as a matter of fact, there was incentive for them to increase costs because that way they could increase their profits. That's the big difference with the commercial crew and cargo program, I think, is that the contracts are structured not as cost plus contracts. So the contracts are structured so that the companies have incentives to be more competitive. So there's definitely policy aspects there as well. I mean, if you look at SpaceX, by comparison, you know, their factory in California, you know, they have basically big chunks of aluminium goes in one end of the factory and a rocket comes out the other end. Like, everything's integrated and streamlined. There's much more focus on efficiency of the actual processes and the business side of it. I think that's the biggest advantage that we have. But the technology is very important as well.
I think I'll make this the last question. My 16-year-old son wants to be like you, meaning he wants to do something related to space. What is most important for him? What does he should study now? I remember you were studying all the time when you were a high school student.
Yeah, I went to high school with RT. Look, I know your son, RT, and I know that he's a very, very smart kid. So I think right now you have to study maths. I mean, maths is really boring, probably at a high school level, but I always get frustrated when I see people talk about high school maths like, oh, I'm never using that. You know, we're never using that stuff. It's not useful to learn it, especially right now. Like, everyone's going back and learning all about exponential growth for the second time. But I'm like, I mean, we use that sort of stuff every day. That's the bread and butter. Those basic science and math skills, which if you look at them on their own, they don't really make sense. And this even extends, I think, into the first couple of years of engineering. You've just learned so much about so many different things. And it's just like, I'm never going to use all this. But then in those last few years of undergraduate and definitely into graduate school, you start to see how everything comes together and how you've got sort of this toolkit that you can sort of take things out of and like, I know how to solve that problem. I'll use this equation or I'll use this formula, this theory. All of that stuff is important. At 16, I think the most important thing is to look at the different fields and try and figure out what you're interested in. You know, study a bit of biology, a bit of physics, a bit of engineering, whatever you're interested in. Find out what you like, because there is a lot you can do. And you don't have to decide right now. I mean, 5 years ago, I was working on helicopters and now I work on rockets. I mean, nothing is set in stone. You just have to try different things and build the skills as you go.
Thank you for your advice, and thank you all for your questions. We would like to wrap up the space talk, and thank you everybody for joining us. In the comment section, we put out a link of Google Forms, and please fill that out for our future improvement. I would like to thank Matt Richardson again for joining us, and thank you everybody for joining on a Sunday. Have
Thanks
a
for
great
having
day,
me.
everyone. Have a great night in the US and everywhere else. And Ad Astra.